All right.
Are you ready?
Yeah.
So I think we will get the show on the road. I think that there's a critical mass to get started. And so good evening. My name is Igor Siddiqui, Associate Professor here at the School of Architecture and Chair of Lectures and Exhibitions, just for a couple more weeks. This evening's lecture, titled Bodies in Formation, will be given by Andrew Kudless. This late in the semester, people tend not to read their emails, so I'm going to feel less bad about reading the text that was also circulated by email, but then also include a couple of my own thoughts. So Andrew Kudless is an architect based in San Francisco, where he's an associate professor at the California College of the Arts. In 2004, he founded Matsys, a design studio exploring the emergent relationships between architecture, engineering, biology, and computation. He holds a Master of Arts in Emergent Technologies and Design from the Architectural Association in London, and a Master of Architecture from Tulane. The work of Matsys has been exhibited internationally and is in permanent collections at the San Francisco Museum of Modern Art, the Pompidou Centre in Paris, and the FRAC Centre in Orléans, France. Matsys is a design studio exploring and expanding the agency of material systems to produce emergent and integral relations between form, fabrication, and performance. The studio works at all scales and pursues a trans-disciplinary practice that blends art, design, architecture, and engineering. Its methods of research focus on the tension between digital morphogenesis and the physical form finding, knowing that each domain contributes essential information to the design process. Craftsmanship in both digital and physical forms is at the core of the studio's research and practice, and this interesting craft, combined with a fascination with the emergence of structure, form, and intelligence in the world, drive Matsys to create object spaces and landscapes that are complex, playful, and a bit uncanny. So every semester, as we plan for our lecture series, we ask ourselves a series of questions about the program that's coming up. And among those questions, we ask, like, why and why now? So why are we inviting our colleagues to speak here and why right now? So why Andrew's contribution to the areas of digital design and fabrication is so profoundly present, especially in academia, but also in practice. Long before, for example, long before cellular resolutions of digital surfaces were achievable with a single component in plugins like Grasshopper, Andrew was researching honeycomb morphologies as a way of bringing together issues of self-organization, performance, and structure, and in this way rescuing digital architecture of that era from its fascination with image and smoothness, and paving a way forward toward innovative methods in computationally driven fabrication. Long before flexible formwork made a comeback in student projects, Andrew was looking in the work of Spanish architect Miguel Fisac and figuring out authentic ways of bringing together the fluidity of digital workflows with the fluid nature of plaster and concrete. And likewise, he was also among the first to produce drawings made by robots that were actually beautiful. And why now? I have to confess that I've been promising Andrew and also our students that he would lecture here for a few years now. But more than ever, perhaps now the timing is really right for architecture and for Texas. Andrew just completed his first permanent building, and we're lucky that it happens to be in Texas. It's a concrete pavilion, the concrete pavilion at Confluence Park in San Francisco, realized in collaboration with Lake Flato. And of course, this is exciting on many fronts, but especially as a tangible demonstration of the potential impact that experimental, research-driven architecture can have on professional practice. Please help me welcome Andrew Kudless.
Thank you, Igor. It's a pleasure to be here. Last time I was here was 4 or 5 years ago for TexFab. Actually spent a week, I think, in this room teaching a workshop. Yeah, it's great to just be back in Texas too and to share with you this recent work. So before I get to Confluence Park, which will be at the end, I want to talk a little bit about how I organize my practice. And it's less of like a conscious way of organizing it. It's more of like a taxonomy, like after the fact, and of just a way I can kind of get a handle on what are the different kind of morphologies that I'm exploring in the practice, but maybe more importantly, than the kind of form of these things and how the taxonomy is created, is that each one of these forms kind of represents a certain kind of conceptual idea within the work. So today I'm just going to talk about 4 of them, just very briefly, for 1 or 2 of them, and the shells and news for longer. And before I get into them, I'll just go through each of the 8 very, very quickly, just 1 slide each. And kind of what I mean by like the relationship between the form, the taxonomy or these morphologies, and the kind of concept behind them. So with shells, I guess I'd say I'm less interested in the form of the shell, but what that form represents conceptually. So in this case, it's like how do we integrate form and structure and material, and what do we learn from this kind of this generation, or maybe a couple of generations before, of engineers and architects like Heinz Eisler, Friato, Felix Candela, and many others, who created these incredibly strong and lightweight structures, and how do we kind of extend their legacy into new digital tools and analysis. With cells, what I've been interested in is how do we kind of work between kind of difference and repetition, of how do we make something that is seemingly non-repetitious, modular, and without, that things that are non-repetitious are expensive, they're hard to build, but how do we kind of approach kind of the aesthetics of some of these things without while still working kind of modularly. With fields, which I'll talk about in more depth in a moment, what I've been interested in is how has computational thinking and art informed each other, and how can robotic control contribute to the production of art, and how do we relearn kind of the generative active drawing in the age of automation. So I've been looking back at a lot of the work of minimalist and conceptual artists from the 50s and 60s, like Solowit, for kind of inspiration and how drawing can still be generative. With stacks, the focus has mostly been on kind of like a self-criticism of a lot of myself, but also of my peers, of the kind of generation of people working in digital design. And a lot of us have kind of often in projects privileged form over material waste, right? Because we can create kind of any form through these different technologies of laser cutting and CNC milling and so forth. We kind of tend to forget that material comes in a certain size, and when we cut something out of a sheet and we're left with 50% of it being waste, that's a problem. So in this area of work, I've just been trying to figure out how do we reduce waste, and how do you maybe start from the size of material and kind of work backwards towards a form. With strands, it's probably the most conceptual, and it's just like how do we work between kind of the singular and the multiple. How does one thing turn into many, and kind of, or how do many things work together as one. With news, it's the focus again is less on the form of the pneumatic or other inflated instead of air inflated with plaster or other materials, but it's just how as a designer do we work between kind of a top down. We're all taught as designers to kind of design in some ways is a top down profession or activity. How do we kind of work between the skills that we have as designers and with kind of more bottom-up emergent processes? And how do we know when to release control to these bottom-up processes? And what do we gain from that? And then the final 2 are more pedagogical and kind of the way, all of these topics inform the way I teach. But with these 2 last ones, it's very directly been generated through my teaching. So with the morphology of eggs, is what I've been focusing on is how do we teach craftsmanship, and how can knowledge of craft, material, and tools inform the design process, and how do we teach the necessary and productive process of failure within the design studio context. So just very briefly, in some of my studios a few years ago, I would ask students to spend the first 4 weeks just researching a way of making something. It could be something they're familiar with, maybe something they're not, maybe they've always wanted to learn how to weld or cast. It doesn't really matter. I just want them to spend 4 weeks making 5 16-inch tall eggs, with the idea that the first one they make, it's going to be bad. It's going to fall apart. It's not going to work. But to not expect everything to kind of be perfect on the first time, and well, perfect never probably, but that each iteration they learn more about the material, more about the technology, and only when they gain kind of mastery after 4 weeks of kind of working, just trying to do the same thing over and over again, do I then assign them like a typical studio project of a site and a program and so forth, and then they're asked to kind of work through their material kind of craft knowledge to develop the program and site design. And then totems, this is more related to how do we begin teaching design. It's like, what are the essential topics of architecture and design? And I began to be quite critical of the way I had been teaching and many of my peers, where somehow we would assign, you know, a site and a program, and there was some magical process that happened, and students would generate a concept that was somehow related to site and program, and then there was a design. And at the end of the term, students would often have no idea what the design was made out of. You know, you'd ask, you know, like, is this concrete? Is it steel? Is it wood? They're like, it's chipboard. I don't know. It's just a form, you know. And I was I wanted to kind of reverse that. So in this process of making these totems, students spend 2 weeks focusing on concrete, on wood, steel, and then sheet material of often wood or paper or plastic, and learning the technologies of those, and also, I should say, in parallel, learning some of the kind of what I've categorized as these kind of 7 essential skills or dichotomies within architecture. So with, for instance, while they're learning concrete, they're also learning about positive and negative space or figure ground diagrams. With the wood, they have to make 200 identical small pieces of wood that then get stacked. So they're learning about modularity, they're learning about part-to-whole relationships, and so forth. So I'm kind of teaching the essentials of design without ever having to talk about site or program. And then only after 8 weeks of this do I then tell them that these are 200-foot tall towers, and they have to develop a circulation system and a program and do sections and so forth about that. So, I mean, they are fantastic in a, you know, they're crazy and that they're not real, you know, skyscrapers by any means, but it still covers, I think, many of the skills that an architect needs of knowledge of construction, of various materials, of form and space, and so forth. Okay, so those were the kind of 8 areas that I kind of try to categorize my work, and some projects clearly fit into one, other projects fit into multiple categories, or have subcategories and so forth that draw from some of these. But it's just a way for me to kind of think through these different streams of work. So with fields, like I was saying, I think there's this issue of drawings used to be the generative act of architecture, that we would sit and we would draw, and at a certain point those drawings would get more and more sophisticated, and those drawings would turn into models, those models would turn into prototypes, they would turn into buildings, but the sketch and the drawing were essential to the generative act of architecture. Now we build digital models, building information models, and the drawings are kind of an afterthought. They're there because institutional bodies need them, permitting offices need plans, they require plans, sections, details, and so forth. Many of our machines don't require any of those. In the future, we won't need them as much on the construction site. With more VR and AR technologies, like the model will be the primary kind of representation of the design. And I think there are some great advantages to that, but I think there's still an issue of where are drawings? Do we just accept that drawings are kind of this afterthought, and they're just there for legal purposes, but they're not really there for any kind of any generative purposes? So in this area of research, what I've been trying to understand are just ways that I can engage drawing beyond it just being an artifact of the model. And one of the ways that I've done that, and actually started here in the workshop that I taught, at TextFab was, I don't know when that was, 2014? Is that 13? Somewhere in there. My colleague and Adam Marcus and I, we were both teaching a lot of Grasshopper, Rhino classes, and we started to get these comments from students where I would say, oh, why don't you do this in Grasshopper? And they would say, oh, well, I don't really know Grasshopper because I don't like twisted towers. And I was like, what? That doesn't make any sense. Like, why did you not learn a tool because you don't like a style? And I realized it was a failure of teaching on my part and on my peers' parts, that the way that we had been teaching these technologies had been through case studies like the Swiss Re Tower in London, or any kind of, these icons of parametricism. And although I knew, and in my own work, I was using the tools in ways that were different from that, I was trying to engage students with these tools through kind of big, iconic projects that used them. And students that were not interested in doing that type of work started to think that there was a very direct relationship between those tools and those buildings or those styles, and would refuse to use the tools because they had no interest in those styles. So as a way to kind of re-engage students was thinking computationally. I kind of, and Adam, we started going back to kind of the work of minimalist painters and artists in the 50s and 60s, like Ellsworth Kelly and Eva Hess, Solowit, and many others, as well as along the bottom band here, a group of computational of computer programmers who had access to computers at the time, who began to do art. So basically, on one hand, there were artists who I would say were thinking computationally, and on the other hand, there were programmers who were thinking artistically. By using some of these as case studies, so rather than teaching Grasshopper through looking at the Swiss Re Tower in London, I would look at a Solowit drawing and say, what's the logic of this drawing? How do we deconstruct it and figure out ways that these drawings could be automated? And explicitly, the reason for that was a lot of Solowit's work was automated. That he literally wrote scripts, not scripts that we think of as computational scripts, but scripts like an actor would have a script. And he would send, like, he thought the reason he's kind of the father or the founder of conceptual art was that his art was literally just a 8.5 by 11 piece of paper that had the instructions to make the artifact that we see in a museum. So that the drawings are actually produced by assistants, by preparators, and so forth. That's not the important part. The part that's actually sold to a client, to a museum, is the generative script. Using this as a way to teach, I thought was really productive. That students kind of get out of the mindset that it's related to a particular style, and they begin kind of respecting the tool or looking at the tool in other ways. So actually at the workshop here, this is one of the projects that we went over. This Solowit's variations on incomplete open cubes. He had a series of, this is Solowit's project, that he had a series of rules of how many edges and how many different permutations of an incomplete cube could you get. And there were some limitations on that there couldn't be less than 3 edges. The 3 edges had to be connected to each other in some way. All the edges had to be connected to each other in some way. They couldn't be rotationally symmetric. You couldn't rotate the cube and call it a different cube. So one of the drawing exercises that I did with students early on was to say, what if we took away some of those limitations? How many incomplete cubes are there? That if a cube has 12 edges and you kind of permutate through all of those different edges, how many different ones are there? And then to use this, the tools to then generate these axonometric drawings. So they almost looks like some foreign language in some way, of this kind of pictograph language or something out of Star Trek or something like that. But they're actually just all axons of a cube. So then I was in Australia a few years ago working, had a sabbatical, and had access to this very large robot that had a 16-foot length of reach. and decided to then draw all of these permutations on a 16-foot by 4-foot sheet of paper. And what I learned through this process, and the reason I chose to do it with the robot was I was really scared of the robot, and I didn't want to start routing anything with the robot until I could understand line weights with a robot. If I could kind of have the sensitivity, if I could understand the kinematics and the sensitivity of the robot with its own kind of body system through drawing, then I felt more comfortable to kind of jump to things that were much more dangerous. And what I learned through that was that one of the ways that you can program a robot is unlike a lot of other machines like CNC routers that are very much like a kind of point-to-point based kind of system. If you guys laser cut anything that you had a curve, and then when you laser cut it, it's like, why does it look all faceted? Is that in that process of sending a file to most machines that needs to create discrete elements out of them, of polylines essentially. And one way of programming the robot, it produces that, but another way of programming the robot, you basically just say, here are the 2 points, the starting point and the end point of the robot, of where it needs to start from and move to. And you just say, move in whatever way is most comfortable to you. So it's like the yoga of robot programming in a way. And that in order to move in a straight line, it actually takes us in our own body a lot of concentration to move in a straight line between 2 points. But if we just say start here and go over here, it's much easier for my shoulder to just kind of arc between them. And in a similar way, the robot, it's much easier. And by easier, I mean less energy, less strain on the motors and so forth. So in this part of the process, I was taking advantage of this other way of programming the robot to just set the kind of points of the axonometric of the cube. And then, so these like kind of curved brush strokes are simply a result of the kinematics of the robot trying to find the easiest path from one point to another. I'm just gonna skip over some of these. You can see how ridiculous it was of like sticking a little brush in the end of a router and not turning the router on. So I did another series of drawings, again, just trying to test out different ideas. Some of them were mistakes that trying to figure out what happened, it was not the drawing that I expected it to be. I discovered kind of more about the kinematics and the programming of the robot. This was another one more recently where I was basically scraping Instagram, geolocation within Instagram, and it was an exhibition in Tokyo. So basically taking images that were being uploaded daily within one neighborhood and then having a robot arm process those images into toolpaths and then paint each image as fast as it could and then roll. So over a course of 2 weeks, it produced about 200 images. And then even more recently, last year, Adam, Marcus, and I curated the Drawing Code Show that brought together 24 different designers focusing on the relationship between code and architecture. Some of it was code in relation to like styles of architecture, like what makes a style, what's one style and what's not a style. Others, it was permitting issues, the codes involved in building codes. For others, it was codes of representation of line weights and others. Others was language within architecture. And for my own drawing, this was right around when Trump was elected, and there was a lot of talk of walls. Walls were just in the atmosphere of everyday radio and television. And so what I wanted to do is I wanted to try to see if I could push a generative process to produce a city that was only a wall. So rather than kind of the walled city that we know of, from like many parts around the world where there's a wall and the city is inside the wall, I wondered if a wall could be a city. Could a wall just grow and kind of take over an area and become everything of a city? So the way that worked is basically I started with a circle and then increasingly increase the length of all of the edges of that circle slowly over time without allowing the edges to intersect each other. So it produces this kind of like coral-like growth where the walls are kind of butting up against each other, but there's almost like a force field around each wall that prevents them from intersecting. until it hits the boundary of the city, which I'll just speed it up. There we go. And it then starts kind of folding in towards the center a bit more. The other problem I had in this, though, is you get this big kind of long ribbon, but then how is this representing a city? Like, how would someone know it's a city? And I knew it was a plan drawing, so I needed some way to populate this plan with elements of a city. So I couldn't. I was trying to figure out how to do that. Like, what programs do we see on the rooftops of a city? So I used Google as like a generator, a different way of generating a program. So I would type in the word rooftop followed by A through Z, and whatever word Google suggests came up with that was the most architectural, I would then develop an algorithm that would represent that program in the drawing. And you can see the algorithm had to adapt to different shapes. So like this is rooftop pool, but this is also rooftop pool, and that's rooftop pool. And so you get multiple programs showing up because of the length, this 10-mile long length. They show up, I think, maybe 50 times each or so. And each time it had to kind of deal with the kind of local site, idiosyncratic elements of the site. Okay, so onto the strands, morphology or morphotype. I'm going to mostly talk about Strand Garden, which is a project I did for Design Miami. It was a commissioned project by the champagne company Perrier Jouet, and it's the only project I've done where it was a branded project, that a brand is basically hiring you to do something that just elevates their brand, gets more advertising, kind of more Instagram hits, more whatever. It was a very strange kind of relationship to have, and that most art and design and architecture the goal is not to just generate buzz in a way, but in this case it was. But they're a very enlightened, I'd say, brand, and they have an amazing collection of Art Nouveau from the early part of the 20th century. And in some multiple visits to the winery in France and looking at their collection, I was just really inspired by many things, mostly the materiality of the fabrication of champagne. And I decided to create this installation at Design Miami that consisted of these 4 different elements. But before I get to that, kind of where some of the morphology came from was early on working with students in Tulane University in Australia, developing this kind of very rigid yet very lightweight triangular box beam, basically. That even though it's made out of super flexible, if you hold one of these pieces out, it just like bends, straight down. But by forcing it into curvature, both kind of in plan and in section, they became incredibly rigid. Like you could walk across one of these little 3-inch beams. So then we took that idea with the students and a firm called Studio Workshop in Australia, and blew it up much bigger for a light festival in Sydney. It's the Harbour Bridge there in the background. And at the same time, or a little bit later, after I got back from Australia, I started experimenting with 3D printing where I could program the G-code directly. So I had avoided 3D printing in my practice almost entirely because I felt like I was, unlike everything else I was doing, where I had a lot of control over the 3D printing process, with the way at the time that most people had been using 3D printing. It was like you just take a solid model and then it slices it up somehow and out comes a 3D printed part. And I felt like I had no control over how that was happening. So in this small project, I started to program the motors directly to kind of weave these different patterns, more similar to how I was programming drawings with the robot. So then I used several of those processes within my design for the Design Miami project, Strand Garden. So the 4 elements were the screen, which is the wooden screen you see in the background, the bench, which are these concrete and oak stools that kind of aggregate into benches. The 3D printed table, and then the 3D printed ice bucket. This is the plan of the installation. The three screens are designed so it can be brought together and they form kind of a perfect circle, or they can be brought up, kind of broken up and turned into three individual screens. First I'll talk about the screen, and it is using a material that I'd used previously in this project for the Pompidou, which is this micro veneer of wood, like a extremely thin, much thinner than normal veneer, and then laminated with thicker paper, and it allows the veneer to kind of do things that a normal veneer would kind of snap, and that the paper takes on, is much more flexible than the wood. And keeps the wood together when it bends, and developed a joinery technique you can see in these three photos that didn't require any glue or anything like that, where the pieces are like these puzzle pieces that just snap together, and you literally just kind of work your way up, almost like buttoning a shirt, and snap the whole thing together. And used a new tool that I hadn't used before, which is a drag knife, which if you guys haven't used one here on your CNC router, I highly encourage you to, because it's basically an X-Acto knife, and just dragging along, and it produces beautiful cuts in wood and paper and so forth. And one of the kind of accidents in a way that happened was because these little tabs had to slide into each other, there had to be enough tolerance, like a small gap that they could slide in, and that produced all of these small little circles moving up the side, which in the end almost looked like these like bubbles kind of rising up the side of a glass of champagne. Each of the strands had a small Arduino type microprocessor within them, and very subtly, this is a sped up time-lapse video, but very subtly over a couple of minutes they would be kind of glowing. So as you looked at it, there was this sense of something shifting, and the idea was to kind of create this clearing in a forest where there were kind of things shifting, like the wind blowing the trees kind of within a clearing. The bench was looking at how do you just produce one singular stool that then can aggregate together. So it's a concrete base that's the color and texture is designed to match the chalk cellars that were used for the champagne. And you can see the generation of that was actually just a tutorial I often do with students of generating these irregular hexagonal tiling patterns, and then it's just based off of a very simple idea that then aggregates to much larger. So by just making one mold, you can kind of aggregate this tile endlessly in any direction. These are we digitally fabricated the positive, then cast plaster negative kind of molds, and then shot thin coat of concrete into each mold, and then joined them together, and then hand packed in a fiber reinforced concrete. And then the table was 3D printed out of 7 sub-tables that each had just one leg, where again, using the process of kind of algorithmically generating the G-code for the printer, you can basically 3D print things that don't exist, let's say, in the computer. So where normally you're 3D printing, you have a model, and then you get this 3D printed object that resembles the model. In this case, there is no model in a way of this form. There was a very simple kind of NURBS surface, but then all of the code just gets generated kind of off of that. So they were 3D printed with emerging objects. A company in Oakland at Berkeley and San Jose State, Ron Rael and Virginia Sanfratello. I got to use their massive 4x8x4 3D printer. And then they're all joined together, and lights are held in the middle of each one with these 3D printed brackets. And then finally, the ice bucket was fun to work on, and that I wanted because the ice bucket was the one that was most closely associated with, physically associated with the champagne, and that it's holding the champagne. I wanted to somehow make the bucket out of some byproduct of the champagne making process. So I found, amazingly, there's a company in Sonoma that grinds up the skins and seeds of the grapes after they're pressed to get the juice out. So the juice goes on to make the wine or the champagne, and often the seeds and the skins just get composted. But this company dries them out and grinds them into flour, and it's used to make gluten-free breads and things like that. And I worked with Emerging Objects again to basically take Chardonnay grape skins, the powder of them, and to 3D print with that powder into the ice bucket. So you can see kind of the process of some of the early little cups, and then these final kind of petals that get aggregated into the ice bucket. Okay, the news. A long time ago, when I first started teaching, I taught a series of workshops at Yale along with Mike Weinstock, who's the head of who was my teacher at the AA and who was teaching a seminar at Yale at the time. And walking to the School of Architecture there was this sculpture that I saw I saw, and I had no idea how it was made. I could tell it was concrete, but I couldn't figure out what the formwork was and so forth. And that got me looking at flexible formworks of the work of Miguel Fisac and others, which I'll show in a moment, or I think I already showed. And so I started to work with that myself. And this is my first week being a professor, and I created this little 6-inch belly button. And it was not at all the smooth, beautiful form of that sculpture or what I was experimenting with digitally. And I was very embarrassed and kind of hid this kind of mistake in my office and worked for like another 3 months trying to get these perfectly smooth kind of digital surfaces that I was generating in the computer, and getting more and more complicated, and it was failing in more complicated ways. And eventually, after like seeing this thing on my shelf for 3 months, I began to kind of appreciate it, and that it kind of, I think, taught me the value of things, outside of the computer, the value of mistakes, and the value of physics, and just looking at kind of what the material wants to do rather than trying to force the material into the digital form that I had been creating. So yeah, this is the work of Miguel Fisac. And when I started to look at some of the form work, so this was a clinic for the Catholic Church, and done in the late 70s, early 80s, kind of the height of postmodernism in architecture. And what I found really beautiful is that he was like hiding these symbols, of the cross and the heart of the Catholic Church, kind of into the formwork pattern. And you see half of the heart there, and then the cross. And that he was just laying plastic sheeting or canvas over these repetitive linear forms. And I began thinking of how I could control some of that digitally. And not have it so repetitive. So in this case, I would start from an image, process that image through a script into a series of points, almost like you're doing a stipple drawing. And then those points were controlled within the script, so they were never closer together than 2 inches and never further away than 8 inches. Because each of those smaller than 2 inches, the plaster was too thin and it would fail, and larger than 8 inches, and the plaster was too deep, and the fabric would rip through. And you'd have a 10-foot wide puddle of plaster on the floor. So through trial and error, I discovered those limits, and I could build those limits back into the digital model, and then cast this is the formwork, and then each time could just peel off the fabric, wash it by hand for a few minutes, and then put it back on the frame, and cast another one. A couple of years later, I then had the opportunity at SF MoMA to do a much bigger version of the wall. And one of the things that changed in that process was in the original wall in 2006, there was this seam going all the way across that I loved the kind of landscape effect of like these rolling hills when you look at it obliquely. But knowing that the gallery at SF MoMA was 45 feet long and 8 feet wide, I knew that you're never going to be able to look at the wall in elevation. You're always going to look at the wall kind of obliquely. So I wanted to try to get rid of that seam so that it looks seamless. So shifted from a rectangular to a hexagonal form, because with the hexagonal form, none of the horizontals line up with each other. You're always interrupted every other one. And also the big shift was, instead of having like very dramatic differences between kind of the denser points, constraints on the fabric and the looser constraints, I did these gradients to produce kind of this almost sine wave of the wall, kind of leaning out above you and then leaning out towards your feet and leaning out above you and so forth. So we then produced 150, I think, of these over 2 months. And it was backbreaking work, because they go between 75 pounds was the lightest and 150 pounds was the heaviest. And they had to constantly be moved around, and all the materials measured properly and so forth. But got the wall done. And you can subtly see in the photo on the left how the walls, kind of the areas that had fewer constraints, the wall pushes out further, and the areas that had more constraints, the wall is more shallow and bumpier, but at a lower amplitude but higher frequency, I guess. And you can see how narrow the space was. The other thing I did was to change the size of the hexagons subtly. So there's actually 4 different sizes, from kind of extra large down to small. So that when you're looking in elevation at the wall, there's a sense that the wall is also kind of undulating in plan at you. That your eye tends to think that all the hexagons are the same, but because each one is slightly different, it produces this kind of optical illusion. Going back to what I was saying about the form, there are these things that I would have no idea how to model, digitally at the time, and that, for everything from like the warp and weft of the fabric that gets imprinted onto the plaster, so that you can get, within inches of the piece and you still think it's an upholstered, soft wall. And there were a couple of times that I would just go to the museum and just watch visitors to the museum interacting with the wall. And there was this one time that this teenage high school student, young man who definitely had too much energy and testosterone running through his system, he was just like shaking. He's like, and I looked at him like, and he's like, I just want to hit this thing. And and I was like, you really shouldn't. You're going to break your hand. And he's like, no, it just looks like I just want to run into it. And so he did, he started touching it. He didn't hurt himself, luckily, but they had to post guards next to the piece because so many people were trying to kind of, fondle it in some way. It was just like this thing that people just want to touch which was great for me. I wanted people to touch it, but the museum didn't want people to touch it because they're like, if people start touching this, they're gonna walk in the next room and start touching the Rothko or something. So, so unfortunately, I couldn't have people touch it in this one, but that kind of generated the idea for the next project. The other thing was, at this point, through using Kangaroo and Grasshopper, I was able to start to digitally model the kind of inflation of these with the liquid slurry. And I did that less for the representational aspect of I didn't really care about having a digital model, personally. It was more that clients were demanding, we want to see renderings. And I'm like, well, how do you do a rendering of something that physically doesn't, I don't know what the form of it is until I make it. Right? You're pouring this liquid slurry in and the fabric is expanding on its own, and depending on where I would pour the liquid and what part it would every piece was different. So it was very hard to kind of do renderings in the normal way that we would do for clients. But it was also very hard to estimate materials, that I didn't know what the volume of these things were. So I began to get a rough approximation, just to do the weakest renderings I could, in a way, to kind of convince the client that I knew what I was doing. And I did know what I was doing, but they needed to see a picture of it to verify. And I needed a model of it to know how much it was going to cost so I could do estimates. So for this client, the FRAC Centre, which I highly recommend you going to if you're in France, and it's probably one of the best museums of architecture in the world. that I was given this site, which you can kind of see this blue line right here, and that there's this new building by Jacob and McFarlane against this old army barracks, which is where all of the galleries are. And the new building is really just the lobby and bookstore. And there's a long hallway that goes between them, and they wanted a piece to kind of draw people down the hallway, and commissioned me to create the piece. So the big change in this was, instead of using the fabric for every single piece and having these 14-inch thick plaster pieces, we cast only 5 pieces out of 30 out of plaster, and then did rubber molds of those 5 pieces, and then shot a thin layer of concrete, and then hand-packed fiber reinforced concrete. So in the end, it's a little over 1/2 of an inch thick, and the rest of it is hollow. So it made it possible to make much, much larger pieces. So they're still about 150 or 75 pounds to 150 pounds, but they're 2 or 3 times as large. So decreasing the total number of parts, and they're all modular at this point. And then using the script, I could kind of very quickly generate different forms and experiment with different patterns in each of these, or I think the one that's up in the upper left here, it's just 5 different pieces, and the pieces are being turned 180 degrees, so it looks like they don't repeat. So these were the 5 pieces, the one rendering that I did. And then the final wall. And what I love about the concrete, it has a much kind of softer look than the plaster. It has almost like this velvet kind of matte quality with the light. So I'm running late a little bit, so I'm going to just jump over these projects. This was a competition I lost for the Renwick gallery, but it kind of fits into kind of scaling up from kind of these wall facade pieces to an entire ceiling. And instead of having the surface fixed in time with the plaster or concrete, the idea was to use a net that's being controlled by motors. So the net is being held to the ceiling, and then those pulleys bring you can see these pulleys bring the cords back to a series of motors at this end. And the motors are being constantly turned on, reversed, and forward, and so forth, pulling the net in different ways. And then these gigantic inflatable balls are inserted into that. And depending on how the net is placed, the balls roll to different parts of the net, forming different cloud formations. So this was the Cumulus cloud formation. The cirrus cloud formation, where you get these kind of bands running across it, and the cumulonimbus, the thunderstorm, where all of them are just bunched up together in the middle, making this very low surface. So it's just like this slowly, basically, piece that is constantly changing above you, and then at times very suddenly changing when a ball rolls from one area to another. Okay, so the last segment of the lecture on shells. So I've been thinking about this for a long time. Like I said at the beginning, of people like Heinz Eisler and Frey Otto, Gaudi, and many others who have used these techniques to basically develop physical form-finding models that are all in tension, that can be flipped, all in compression. And I began working with these in 2011 at a workshop I taught in Hong Kong, and finding ways to simulate the surface and then tessellate that surface back into parts that could be assembled into the shape. And then working with students at the University of Minnesota in Minneapolis to do a 4-day workshop where we went from no one having any experience with the software to, after day 1, they all had kind of a tutorial on the software. They then, on day 2, competed in a competition against each other to develop designs in different parts of the architecture school. And then at the end of that day, we picked a design, and then days 3 and 4, we fabricated it out of like $200 worth of cardboard. And then a few months after that, based on the success of that project, I did the Shell Star Pavilion with Riyad Juka in Hong Kong, which this is the only photo I had of the site, which is a typical Hong Kong site where there's no sky, there's only towers. And I knew it was only going to be there for a few months before a hotel was going to go in. So this was a very temporary pavilion for just a few weeks for an art and design festival. And I literally had no information about the site other than that one photo. And when I asked the client, like, what's going to happen during this festival? They said, we don't know. I was like, are there going to be performances? And they're like, we hope so, but we don't know. We're still like hiring people. And I was like, is there a bar somewhere that the pavilion, like, where is I didn't understand anything about the site. And they said, this was like 2 months before the opening. They're like, you're the first person we're contacting, and it needs to be done in 2 months, and that's the only information you have. We just want it to get people to come to the site. So it was a very weird design brief, and there was nothing to respond to other than attraction, like make something that pulls people. So literally the concept was just a point in space, and people are kind of being sucked to that point. So I started with that. I made a very simple series of triangles that kind of pinwheeled around that movement, subdivided it, and got the kind of dual of that subdivision, going from triangles to hexagons and pentagons. Simulating the mesh, optimizing the planarity of the mesh so that all of the hexagons were planar. Checking, working with David Shook from SOM, Structural Engineering, on making sure that the in-plane forces were as in-plane as we could get, so that the shell could be as thin as possible. And then developing the fabrication data to unroll and unfold all of the cells, and then cut them out of coroplast, and on to like figure out how do we even know where this column should be, developing kind of just drawings on setting out how we could just lay everything out with string and a tape measure. And then the final piece, and I was just mentioning this earlier right before the lecture started, that so this project, like Confluence Park, is definitely dealing with rain. I learned a lot about rain in this project, in that I thought using coroplast would be good in a hot, humid, rainy environment of Hong Kong, and that it's plastic and the water would just run off of it. Not thinking that coroplast is actually hollow, and through capillary attraction, any water that runs off of the edge immediately gets sucked back up into the interior of each sheet. So we calculated that it actually weighed, the weight of the rain sucked into the inside of the structure weighed 4 times as much as the actual structure itself. So after a couple of days of rain constantly pouring on it and it sucking up more and more rain, the shell started to sag a little bit, and we had to come back and put these PVC and then steel conduit kind of reinforcement arches up to just hold it. So it was a little unfortunate, but yeah, my first experience dealing with rain as a design generator or a design destroyer, maybe. Okay, and then most recently at UVA, doing another student workshop of a series of shells where in section each of these are like a section across this leg is basically 2 triangles and then another triangle facing the other direction. So if you cut a section through that, it would look like a truss. So it's a series of basically trusses in one direction and box beams in the other direction. Okay, so finally, Confluence Park. I think I have a few minutes left. Confluence Park started well, many years ago. I'm learning more and more about it now that the project is at the opening. I learned more about it, and that everyone was like competing on who could say how long they had been involved in the project. My involvement is only since August of 2014, so 3.5 years. But some people, go back 10 years and like acquiring the site. And there was a previous design team on the project before us, and Lake Flato, local architects in San Antonio, and they have an office here now as well. They approached me to go in together on the project, and that the client was asking for a local firm to partner with an outside kind of more experimental design practice. And Lake Flato was generous enough to invite me to be on the team, along with architectural engineering collaborative. Tyler and Chuck are here from AEC, and it was fabulous to work with them. and Rialto Studio was the landscape architect, and the client was the San Antonio River Foundation. The project was to develop this site that was a parking lot for the local utility company, I think. And it was to develop it into an educational park that basically mostly served elementary and middle school students in teaching them about water conservation and the various ecotypes of the region, from kind of West Texas to kind of Central Texas and then along the coast, as well as the river ecosystem along the San Antonio River. So it's called Confluence Park because it's at the confluence of the San Antonio River here and the San Pedro Creek here. And in the early design meetings with the client said something that at first we all just laughed at it, but after a couple of months of thinking about it, it really stuck with me and generated the design of the pavilion. In that they said, we want this to be, like, we know this sounds crazy, but we want this to be the type of park that when it's raining, you look out your window and you see it's raining, you're like, hey, honey, get the kids, it's raining, let's go to the park. And they admitted that it sounded crazy, and like you would never normally go to the park when it's raining. But the client was so passionate about the importance of water conservation and water and the watershed in the region that they wanted to kind of celebrate rain as an important kind of environmental event in the landscape, and an urban event. So the original kind of concept design was a kind of a shed roof, like a big kind of curving shed roof, like an umbrella, like a lot of projects, of architectural projects, that the goal is to get the water away from the building as fast as possible. And after hearing the client say that they really wanted to celebrate rain, I started to look at other systems, other forms, and how they deal with rain. And a lot of plants actually, kind of like calla lilies and many other plants, agave and many of them, where they actually, the petals of the plants, they kind of reach out and then cup, not only for kind of structural reasons of the curvature, but also just to kind of pull the water to the root stem. So you can see some of these succulents and hosta and other things. So this was one of the design development renderings of the idea of these gigantic funnels that basically celebrate the rain event, and kids could kind of go into the funnels and have these kind of waterfall falling on them. There were some ideas that in the end the client didn't do. So the renderings, you'll notice that the outside is brown or reddish color. And the idea was to broadcast out, spread out little bits of iron into the concrete when the concrete was still wet, so that over time the top surface of the water running across it would rust the outside surface, while the inside surface would stay light gray. So in figuring out how that rain flow system worked, I used a simulation to basically simulate how rainfall would hit the surface of these curved petals and then run into these valleys and then end up in the base of each column. So that I would do this and then go back and adjust the curvature of the parametric model of these surfaces so that the rain would then flow in the proper direction. The other issue around the geometry of the pavilion was we knew that actually it was Chuck's idea to make it out of concrete. Early on it was wood, and then it was wood and fabric, and then it was steel and fabric. And at one point Chuck said, I think this just needs to be concrete. And I'm so thankful to you, Chuck, for that, because it did need to be concrete. And but when working with concrete, a lot of the cost is in the design and fabrication of the formwork. So we knew it had to be modular in some way. And when we started working with various systems of equilateral, triangular grids, square grids, hexagonal grids, for the tiling of these modules, the petals, The problem was that no matter which way you looked at the pavilion, it always looked the same. It was just this endless, the grid of columns. So by shifting to a pentagonal system, the problem was the pentagons don't tile with each other. Regular pentagons don't tile with each other. But by shifting to this irregular pentagon shape, and then breaking down each of these pentagons into, so here's that pentagon again, breaking it down into 5 triangles where there's one equilateral triangle and then one asymmetric triangle that's then mirrored to produce its neighbor. So there's basically 2 A's and 2 B's and 1 C petal for every pentagon. And then laying that out and taking an irregular kind of outline around all of those, where basically across each of these, it forms an arch. From an A to a B, it forms an arch, or from a C to a C, it forms an arch. That you can kind of carve out this irregular shape, and it's the grid of the structure is not very obvious. So this is the entire park. Each park is divided into different sections. This is more of the Trans-Pecos desert. The San Antonio River ecosystem is along the edge, right, reaching down to the river down here. There's the kind of central Texas kind of grasslands in the middle, and then kind of oak tree forest on the other edge of the site. There's then a multi-purpose building that has bathrooms, public restrooms, and a classroom / conference room space, as well as a storage room for chairs and tables and so forth. And then the pavilion along the end. In addition to the pavilion, there are 3 smaller pavilions that provide shade throughout the site, so that as school groups go and move around, they always have shade near each of the ecotypes. I should also mention that all the water running off of the pavilion then gets collected in below the structure and then redirected into a cistern that's below this area here, and then the water from that cistern is used to irrigate the vegetation throughout the site. This is the plan a little bit closer in of the pavilion. And then I just very briefly mention another way that that pentagonal tiling came back into the project, and that we designed these pentagonal tiles. So this is one of the tiles. We did 4 different variations of 4 different kind of inlay patterns, so that when the tiles are put on the ground, the workers just kind of randomly put them in different arrangements, but the pattern, they're always connected from one to another. So you can see that here. So it does 2 things. You get this kind of endless series of confluences of the inlay pattern, and the kind of the hexagonal or pentagonal. You can either see the bigger hexagons or the smaller pentagons. That tile pattern kind of disappears, and your eye starts following kind of this almost like delta of lines. And the other thing that I thought was really interesting, and I hadn't thought of until the landscape architect showed it to us, that you could kind of, instead of cutting the tiles at hard edges like they do sometimes here, like in this case with the brick pattern, often they just leave the pattern kind of, they just remove tiles and allow gravel or wood chips, mulch to kind of go in, and it produces this really, I think, beautiful kind of edge condition where plants start growing kind of all around that. So then we got into how to fabricate it, and I think this is one of the really interesting stories about the project, and that once the contractor was selected, they approached a couple of formwork fabrication companies that would produce formwork out of plywood, and the first bid came in at more than the entire budget of the project. And I thought I was going to be fired and we were going to have to start over again or something, because it was like, how is this possible? That's the material, the formwork is thrown away after a project. Like, how is it possible that this waste material costs more than the entire project? And it was a ridiculous number that I think these companies threw out because they were so scared of the geometry that they didn't know how to do it, and it was just going to take too much time to do it in traditional techniques. And I advocated for the contractor to approach Chrysler and Associates in near Napa, California. And I'd worked with them in the past on school projects, academic projects, but never on a professional project. But I knew that they love just weird stuff and that they are not scared by strange things. They do a lot of work for artists that do, like, for instance, the giant blue bear in Denver, or just other strange forms, and they love that. So their bid was much lower than like by an order of magnitude lower than the traditional fabrication technique. So by using robots and giant 5-axis routers and so forth, they were able to mill out a positive of each of the 3 petal types of A, B, and C. About a, I don't know, 3 or 4 inch, 2 inches altogether, or 2.5 inches of basically an 1/8 inch layer of fiberglass, followed by 2 inches of balsa wood, followed by another 1/8 inch layer of fiberglass makes up the thickness of the formwork. So this is all balsa wood, so lightweight. It's basically just taking the 2 strong things, just like a truss or an I-beam, of taking the 2 pieces and separating them, and then filling the space in between with very light material. Makes this super sturdy, rigid formwork that could then be reused again and again. So each piece had to be reused around 10 times for the 10 or so petals of each type. So you can see the petal, it's like a modified tilt-up concrete technique, where tilt-up walls, you usually cast them on the ground and then crane them into place to make like big Home Depots and Walmarts and things like that. In this case, the final shape is like this, but they were cast like that so that the whole top surface could be simply broom finished, and we didn't have to fabricate formwork. So it's like half the amount of surface area to do this. So you can see it was just broom finished on the top with, and then after they're set, they're then 2 cranes position 2 opposing petals. And again, AEC, Chuck and Tyler had amazing idea to simplify this, that I went into this thinking that we should have like all of these petals tied to each other, and that would make it super rigid. But they had genius idea of just making each opposing petals just a simple arch, and that way, if there was any deflection or settling of the petal, they're not pulling its neighboring petal with them. And there's literally a hinge at the top of each arch where the structure can kind of move if it needs to. So you can see what's going on with that the formwork was just incredibly beautiful, I think. It just looks like this car body. And there are a series of these PVC pipes that we inserted into it that then produce these very small skylights, so almost like this field of stars above your head. And then this is the final pavilion, here seen from inside of the classroom. And they're going to be hosting free summer camps all summer, that they got enough fundraising not only to fund the construction and design of the building, but to fund camps all summer where students will like go down to the river and collect river water and look at it under microscopes in the morning, and in the afternoon they do art based on what they saw in the water. And it's been, I just have a couple more slides. It's been a pleasure to just finally have this project done. My involvement was mostly, 3 years ago, 2 years ago. So to have Lake Flato and everyone on the project over the last couple of years getting it actually done has been amazing to just see now that's finally done, how people are using it. There are things that I expected and I wanted to kind of happen within the space, of people, riding bikes through or just playing. Like I specifically designed the column, the gap between the columns at the base to be 16 inches apart. So it's actually a little too small for an adult to go through, unless you kind of shimmy sideways through it. But kids love, finding, like my daughter called it the secret room. There's only one column that is completely enclosed. Big events like the opening or this yoga or weddings and other parties, that are starting to happen there. But then more unexpected things that, just controlling Instagram. You just see these things that are like, I had no idea. Like, I didn't even know what Fiesta was, and there were these medals or whatever being created of the park, and people going there on weekends and painting, and Michael Jackson impersonators doing drone videos of it, and light installations and things. It's just been amazing to see how people kind of are being inspired by it and making it part of their own community. So I think that's it. I'll just leave it with this video. So thank you very much.